แล้วเขาเกิดมหกรรมอะไรกันครับถึงลากันเยอะอะไรขนาดนี้อ๋อเมื่อวานมันเหนื่อยอ๋อที่บอกว่าคุณมีอะไรนะทำพิธีไหว้ครูอะไรกันอย่างนี้ใช่ป่ะโอ้ไหว้ครูแล้วสอนเลยอ๋อครับจริงครูโคเขาก็แจ้งผมแล้วแหละว่าอาจารย์ไม่ต้องมาแต่ว่าก็อะไรอะดร.โชคครับเขาบอกว่าต้องมาเพื่อว่าตามกฎระเบียบอะไรอย่างเงี้ยครับต้องมาที่ห้องจริงอะไรอย่างเงี้ยแล้วคุณไม่เหนื่อยหรือว่าบ้านคุณอยู่ใกล้เดินทางไม่เหนื่อยหรือว่าไงอ๋อก็เลยจะเป็นต้องมาใช่ไหมครับอ๋อมีประเด็นอะไรอ๋อเป็นแบบโรงเรียนเกณฑ์คุณไว้อย่างเงี้ยเหรอหรือว่าไงครับอ๋อเขาขอแรงคุณไว้เนาะเราพอไม่ให้ออกอีกใช่ไหมครับสุดยอดมากผมก็ว่าแล้วทำไมพวกคุณอะไรนะรักครอบครัวยังเลยธุระกับครอบครัวเยอะมากเกือบทุกคนเลยซึ่งมันไม่เป็นอย่างนี้ไงปกติมันจะมีแค่คนสองคนอะไรอย่างเงี้ยโอ้โหก็แปลกใจแล้วว่าเกิดอะไรขึ้นกันนะพวกห้องสีนี้เงียบเลยนะครับมียื่นแค่คนที่เข้าไปอะไรนะค่ายอะไรสักอย่างแค่คนเดียวนอกนั้นผมก็นึกว่าจะมาปกติโอ้ HDMI โอ้อันนี้ผมลืมไว้ห้องนี้วันนั้นตายแล้วน่าหาไม่เจอLet's talk about this ต้องเปิด power ใช่ไหมครับเปิดเขาเปิดยังไงครับมันต้องเปิดอะไรนะตัวนี้ออนก่อนหรือเปล่าอันนี้หรือเปล่าครับใช่นี้แบบเบรกเกอร์ก่อนหรือเปล่าผมก็รอตั้งนานไม่ขึ้นอ๋อต้องยกเบรกเกอร์ขึ้นก่อนอ๋อแสดงว่าเมื่อเช้านี้ก็ไม่มีใครใช้ห้องนี้เลยมาสอนอย่างเงี้ยครับถึงไม่มีแบบใครดึงเบรกเกอร์ขึ้น โอเคเริ่มกันที่ยังไงดีครับห้อง4ก่อนแล้วกันมีคนเดียวนะครับเดี๋ยวผมจะได้ติ๊กผมถามในกลุ่มไลน์เขาเหลือใครไหมครับเขาบอกไม่เหลือเลยคนตัวใหญ่อ่ะชื่อทีอ่ะแต่ยังเหลือใช่ป่ะครับกลับไปแล้วใช่ป่ะ
เขาเจออาจารย์โคผมอ่ะแล้วผมไปเจออาจารย์โค
ห้อง4ใช่ป่ะ
โคห้อง5เลย
โคห้อง5ตัวเล็กๆนะที่อ๋อครูที่ปรึกษาคุณโอเคเนี่ยไม่มีใครแจ้งเลยนะครับมีแค่คนเนี้ยที่ไปอะไรอะสัตวแพทย์นักรบใช่ป่ะเขาชื่อนักรบใช่ป่ะคนเดียวนะครับที่แล้วก็คนนี้สันตพัฒน์บรรยากาศค่ายก็ลงไว้ให้แล้วนะครับใช่ป่ะยังไม่ได้สันตพัฒน์ว่าสันตพัฒน์แล้วก็คนนี้หมายเลข5นะครับหมายเลข5เวทแคมป์นะศิลวิทย์คนนี้ไปค่ายบ่อยๆนะครับเวทแคมป์ของคุณชื่ออะไรครับกรกรหมายเลขท้ายๆเลยใช่ไหมครับได้ติ๊กให้นะคนอื่นที่เขาไม่ได้ส่งใบลาก็มีสิทธิ์ขาดได้นะครับโอเค604
ส่งเวลาแต่ไม่ได้ออก
ส่งเวลาแต่ไม่ได้ออก
ต้องไปอาจารย์เขาให้ออกแบบเราไม่โชคไง
นั่งรถผมได้ครับนั่งรถแล้วก็ออกไปเลยปิดประตูไว้ไม่ให้ก็ไม่รู้ครับเขาให้กี่คาบสอนเสร็จก็ตามนั้นนะครับ
โอ้อาจารย์สอนเสร็จไปเลยอ่ะผม
next one we go to M605 right hereโอเคคนไหนที่ไม่ได้ยื่นใบลาแล้วจะติ๊กไว้ไหมครับมีคนไหนเอ่ยคุณได้ยื่นใบลาไว้ปะคนนี้ครับยื่นไปแล้วใช่ปะ
ทุกคนแล้วตอนนี้
ยื่นหมดแล้วทุกคนแล้วผมก็ไม่ต้องเช็คอะไรแล้วดิเพราะว่าก็ถือว่าปรากฏตัวนั่นแล้วคุณโอเคงั้นผมไม่ต้องติ๊กเนาะหรือว่าจะติ๊กว่าใครมาอยู่หรือไม่อยู่หรือว่าไงครับติ๊กก็ได้ใช่ไหมเยี่ยมมีข้างอันนี้หมายเลขอะไรบ้างคุณบอกเลยผม16แล้วก็24แล้วก็9โอ้เดี๋ยวแป๊บนึงนะครับ
วันนี้ยังเป็นคืนเลยมาเรียนแล้ว
9นะครับอนิวัฒน์แล้วก็16แล้วก็24นะครับคนนี้แบบที่เขียนบอกว่ามีธุระอะไรนะสำคัญมากอะไรของคุณ สุดยอดมากคนอื่นเขาธุระครอบครัวนะของคุณนี่ธุระสำคัญมากนะครับผมก็ต้องสอนเนาะเพราะว่าตามหน้าที่เขา ให้อันนี้นะครับไปเรื่อยๆนะครับคนไหนขาดลาก็ดูเอาเองนะครับดูในคลิปหรือว่าอะไรเอาเองครับหรือว่าถ้าจะให้ออนไลน์ก็แจ้งเพื่อนนะครับที่อยู่นะโอเคwe continue our lecture on this person his name is Weber okay which is the unit of magnetic flux right magnetic flux density has the unit of Tesla โอเคเอาเลื่อนได้ไหมไม่ยอมเลื่อนนะเลื่อนมือแล้วนะครับโอเคเอา The way to get the unit is the following according to the SI system one phi is BA right the unit of magnetic flux density is Tesla 1 Tesla and unit of the area is 1 square meter and the SI unit of Tesla is Newton per ampere and meter and you can cancel m square right m with the power of 2 and m at the denominator we're going to have one remaining m at the numerator and we're going to give the honor to Wilhelm Weber the person here เขามีการประชุมอะไรนะล่าสุดเกี่ยวกับพวกเขาเรียกว่าอะไรครับโนเบลคุณได้ดูหรือเปล่าใครได้ดูไหมครับ YouTube เขาเอาพวกโนเบลทางโดยเฉพาะฟิสิกส์เรามานั่งล้อมวงคุยกันนะครับก็มีคนไปคอมเมนต์นะบอกว่าโอ้น่าจะให้พวกนี้นั่งคุยกันนานๆหน่อยจะได้ฟังวิสัยทัศน์ของเขานะครับผมยังไม่ได้ดูจนจบนะครับแต่เห็นว่ามีอยู่นะครับเดี๋ยวเสาร์อาทิตย์ไปนั่งดูนะครับโอเคyeah he is one of the great person who investigated magnetism and electromagnetic telegraph together with Carl Friedrich Gauss you know Carl Friedrich Gauss right he is quite famous in mathematics well yeah 1 Newton meter per ampere will be known as 1 Weber we're going to use the letter W the capital W and small b that represents Weber okay Weber okay and here is the first scenario when the angle between the normal vector of the plane lies in the same direction as the magnetic flux density B. Okay, the normal vector of A is also in the horizontal and with the same as the magnetic flux density in the horizontal direction. And you can see that the two vectors that are pointed in the same direction, there will be no angle between them at all. So phi is 0. And once you substitute phi as 0 into this formula, of course, cosine of phi will be cosine of 0, and that's equal to number 1. Right? So BA times 1 will remain only BA, and this is the optimal case, okay, that we can get magnetic flux when your observation area is perpendicular to the direction of the magnetic flux density. In this scenario, once we move A, which is the area, to the left-hand side, the multiplication term will appear as the division term, right? So we're going to have B equal to phi B by A. Yeah, if we go back to the unit of Tesla, we're going to see that 1 Tesla can be called from, can be derived from this expression, this formula. Unit of phi b is Weber, and the unit of the area is square meter, right? So we're going to have 1 Tesla equal to 1 Weber per square meter. That's quite easy, right? Let's consider the general case when the normal vector of this plane, this area, is not in the same way as the magnetic flux density direction. So we're going to have จิ้มที่ปูนได้นะครับแต่จิ้มที่จอแล้วไม่ขึ้นนะครับอันนี้นะก็มือไว้นะครับโอเค the angle phi has a certain value which is not zero according to this figure, and yeah, this will be in the general expression. Phi b will be ba cosine phi. Let's consider the worst scenario when the plane lies in the same direction as the magnetic flux density B, okay, vector B. We can see that the normal vector of this plane, the area A, is perpendicular, okay? It has the right angle or 90 degrees between the normal vector of this plane and the magnetic flux density B. So phi is equal to 90. Let's get back to the basic or fundamental of trigonometric function. Once the argument or the angle inside cosine is 90, what is the outcome? Cosine of 90 will remain 0, right? So the product of phi b equal to BA cosine phi, right? Once this term is 0, okay, the whole multiplication here, the whole product will also be 0, right? So that's why we cannot observe the magnetic flux at all in this scenario once the plane of this area lies in the same direction as the magnetic flux density B. Okay, phi b is 0. Now we arrive at an example. We will calculate the magnetic flux phi b. Okay, a plane surface with area 3 centimeter square centimeter. The tricky stuff in this problem is that you need to be able to convert the square centimeter to square meter, right? We're gonna go back to the scaling manipulation in prefix unit in physics, right? 1 centimeter is equal to 1 or 10 raised to 2, right, of meter. So 1 square centimeter will be 10 to 2 meter, right, with the power of 2. So you can see that this will be 1 cm square, right? And this one will be 10 to negative 4, right, of meter square. So you can see that 1 square centimeter is equal to 10 to negative 4 meter, right? So now, whatever number they say in a square centimeter, we will be able to convert it to square meter right now. And then the angle is 30 degrees. So phi b, oh sorry, phi, the angle phi is 90 degrees, right? I'm not sure. In a uniform magnetic field that is oriented at an angle of 30 degrees, phi is not 30, we're going to need to write down the actual alignment of the plane. อันนี้คือปากกาอะไรครับเนี่ย
บอกแล้ว
แล้วจะให้ผมทำไงเนี่ย มันต้องเอาทินเนอร์ว่าหรือว่ายังไงครับ
จานคือมันประกาศทุกเลย
ไม้ก็
ประกาศทุกอะไร
อันนี้มันยังพอได้ใช่ป่ะปากกาเก่าผมเนี่ย
ไอ้เนี่ยประกาศมันนั้น
เอ้าไอ้คิดนี่เหรอ what the fuck
แล้วทำไงอะแอลกอฮอล์หรือทินเนอร์จะออกไหมครับเนี่ยไม้ก็
แอลกอฮอล์ออกเนี่ยแต่แบบจานไม่มีทิชชู่เลย
ผมมีทิชชู่เปียกแต่ติดอยู่ในรถหรือว่าในนี้ไม่รู้นะนี่ทิชชู่ครับเปิด
ไม่ต้องทำลายก็เหมือนว่าลายก็มันเอาปากกา
เขาเปิดยังไง
กูไปปลาแล้วปลาไปไหนปลาแล้วตาเขียนเกี่ยวไว้เขียนตรงนี้ก็ได้เขียนตรงนี้ก็ได้
เขียนในจอใช่ป่ะแต่ยังไงก็ตามมันก็ต้องใช้อยู่นะแล้วคุณจะปล่อยให้มันแบบคาจนถึงรุ่นน้อง10 ปี 20 ปีแบบไว้ผ่อน
จะส่งทอด
ส่งทอดไปเลยนะเป็น
เหมือนที่รุ่นพี่ส่งให้ผม
โอเคอันนี้
รุ่นพี่
ถ้าเอาออกด้วยได้ก็ดีเดี๋ยวผมจะพยายามลองเขียนจอนะโอเคyou need to draw it yourself let's say this is the area right and ออกไหมครับ แล้วยังไงพกมาเองหรือว่าไงครับปากกาเนี่ย โอเค anyway 30 degree right so
เขียนจากแก้วด้วยดิ
we're gonna draw the direction of the magnetic field of magnetic flux density like this okay then we need to further draw the normal vector of this plane. This is normal vector. Okay, and the plane direction is aligned by 30 degrees. 30 degrees here. Okay. ก็เวิร์กดีเหมือนกันนะอันนี้นะครับ Okay and but phi is the angle between the normal vector and the direction b right this is the direction b and the vector b okay so you can see that this angle the remaining angle here is phi and phi could be found from 90 degrees minus 30 degrees, right? That's 60 degrees. Okay, phi is 60 degrees and yeah. So according to the first question, what is the angle phi, right? So we will be able right now to say that angle phi, the first question, phi is 60 degrees according to what we draw and we make the subtraction here, right? For the second question, if the magnetic flux through this area is 0.9 milliweber. So they say what they say here is a phi b, right? Phi b is 0.9 0.9 milliweber, right? So you can also simply convert it to the typical Weber unit, right? By using the multiplication of 10 to negative 3, right? That's Weber, right? So that's in right now in Weber typical unit. So what is the magnitude of the magnetic field? So what is B, right? They want to know. Want to know what is B, right? In the second problem. Here you can start from phi B equal to B A N cosine phi, right? B A cosine phi. But the question is, what is B, right? So what is B in this scenario? You're gonna solve this equation for B, so you need to move A cosine to the left hand side. So B will be phi B by A cosine phi, right? Yeah. So let's compute right here in the empty space. B will be phi B, right? Phi B is right here 0.9 times 10 to negative 3. That's in Weber. And A is the area, right? We have already tried to convert the 1 square centimeter to square meter by the factor of 10 to negative 4, right? So we would have here 3, oh sorry เอาเวลากดกลับนี่มันมีเสียงด้วยนะครับ 3
มีเสียงทุกอย่าง
มีเสียงทุกอย่างเลยโอ้ออโต้มาก 10 to negative 4 and then cosine, right? Cosine of 60, which is only 1 by 2, right? This is 0.9, and once we move the term here, it's going to be 10, right? 10 and 9 and 3. This is 1 by 2. Once we flip the number 2 to the numerator, we're going to get 3 times 2. So this will be simply 6 Tesla, all right? This is 6 Tesla. So here we have B equal to 6 Tesla. Please write down also the unit. Okay, 6 Tesla. Let's check whether it's correct or not. Okay, phi B is 60. B is 6 Tesla, right? It's correct. โอ้มันคนละจอกันเลยแล้วเราจะลบที่เขียนนี้ออกไงครับ
อาจารย์อยากให้มันอยู่ไว้หรือลบเลย
จะต้องการลบแล้วหรือว่าคุณต้องการให้ผม export PDF อันนี้ให้คุณว่าหรือว่าไม่เอาหรือว่ายังไงที่ผมแสดงวิธีทำให้ดูเนี่ยคุณต้องให้ผม export ให้คุณว่า
อาจารย์ลองเลือกเลยเดี๋ยวผมลองเอาตรงนี้
อันเนี้ยถ้าแคปหน้าจอครับส่งไปที่เซฟแอดใช่ป่ะต่อเน็ตได้ไหมครับต่อเน็ตผมก็ได้ส่งไปในไลน์คุณเลย
เดี๋ยวผมเอาเป็นได้ไม่เสร็จ
มันต้องเซฟแอดก่อนใช่ป่ะยุ่งยากครับ
เรื่องนี้มันไม่เรื่องนี้มันน่าจะ
ทำไมโรงเรียนไม่มี Wi-Fi ต่อเชื่อมอัตโนมัติไว้เลยให้เนาะ
มันมีครับแต่ไฟโรงเรียนมันยุ่งยาก
เพราะว่าสมัยปัจจุบันถ้ามันไม่มีอินเทอร์เน็ตมันก็อยู่ไม่ได้แล้วโลกมันเปลี่ยนไปแล้วนะครับ
ค
นี่ไง screen capture copy to right?
ฮัลโหล
ไม่ขึ้นใช่ป่ะยังไงดีถ้าต่อ USB ผมมันจะเห็นไหมจะเห็นที่เครื่องนี้ไหมครับมันมีสาย USB ด้วยนะเนี่ยครับเสียบ cover ให้เขาสักหน่อยครับ
ปกติขึ้นเปิดมา
ไม่เป็นไรก็ได้ครับ ไม่ต้องเซฟก็ได้ช่างมัน
เซฟไม่อยู่แล้วแต่แค่จะออกมายังไงเดี๋ยวอีกเรื่องนึงก็ลงเลย
ลบเลยครับ เพราะว่าไปโจทย์ถัดไปแล้วครับ โอ้ดีมากเลย ไม่ต้องใช้ปากกาเคมีแล้วทีนี้ แต่ว่าเอาออกยากครับ เอาออกจากเครื่องยากอันนี้นะครับ Okay, let's talk about the next example นักฟิสิกส์จะเก่งก็เมื่อเราทำโจทย์เรียนครับ Okay, the second problem which is taken from the book number 2 and it's conducting a circular loop so it has the circle shape okay it's circle shape like this radius is 0.25 so this is r equal to 0.25 meter okay and place it in the xy plane with the uniform magnetic field 0.36 there will be B okay B which is 0.36 Tesla okay and that points in the positive z direction this is the xy plane xy right xy plane set in the positive way like that oh. The next one วิชาอื่นเขาใช้พวกไวท์บอร์ดอย่างนี้ไหมบ้างไหมครับเขาใช้เหมือนกันไหมเขาเขียนอะไรบ้างไหมวิชาอื่นแล้วก็พูดตามไม่เขียนอะไรอย่างผมเนาะโอเคผมมันต้องโซฟให้ดูไงไม่เป็นไรครับ calculate the flux magnetic flux through the loop so yeah of course we're gonna follow the same way we in this problem we're gonna need to use the phi b right we need to use the formula phi b is ba cosine phi right b is what we have got here right 0.36 and this conducting loop lies in the xy plane so if this is z axis and here is x axis and here is the y axis okay x y z and the conducting loop which is denoted by the blue one lies in xy plane like this please note that the are in the positive z direction I'm sorry for that okay this figure is wrong we're going to write down somewhere else this is z axis and here is y axis here is x-axis, right? And the connecting loop, which is denoted by the red one, okay? And the magnetic flux density is directed vertically along the positive z-axis direction like this. This is B. You can see that the normal vector of the plane of this conducting loop is also directed in this way. This is N. So the angle between the black arrow and the green arrow will be 0, right? So phi B in this case, phi in this case is 0 degree or 0 radian, whatever you can see. The next one is that we're gonna need to follow the first question, and they want to find phi B. So B is something like that, 0.36, right? Phi B will be 0.36, and the next one is A, right? A is pi r square, right? Pi r is 0.25 times 0.25 square, right? Pi r square. And cosine of 0 will be number 1, so it doesn't matter. So, but the result here cannot be computed easily by using only hands, right? We're gonna need to, we're gonna need to use the calculator, okay? So after the calculation, pi r square, right? We get 0.07 approximately. It's equal to 0.07. The unit of the magnetic flux is Weber, right? Something like this. In what is the change in the flux due to the rotation of the loop? Okay. Let's talk about the second one first. One is the loop is rotated clockwise. Clockwise means in this way, right? By 45 degrees. So recalculate the magnetic flux. So we're gonna compute it again, but the angle here is no longer 0, right? It's phi equal of 45, right? So phi B in this scenario will be 0.36 and pi again, right? Pi r square, which is 0.25 square, and cosine of 45 degree. Okay, so we need to use again the calculator. It's going to be only 0.05, okay, approximately 0.05. Weber. And the difference, okay, in the third question, they want to know the delta phi B, right, which is the final state subtracted by the initial state, right? So phi at 0.05 minus 0, the initial state, right, 0.07. So it's going to be negative 0.02 Weber, okay, or 20 milliweber. Okay, let's check whether our answer is correct or not. Yeah, approximately 0.02 Weber. แล้วเคลียร์ไงครับเคลียร์คือปิดอันนี้เลยใช่ไหมครับเคลียร์ที่เขียนเนี่ย
ที่เขียนก็ถ้าอาจารย์อยากเซฟก็
เซฟ
เซฟไว้อันนี้
จะเซฟก็ได้ฮะเซฟโอ้ my god
กลับไปอีก
กลับไปหน้านี้ใช่ไหมครับ
ผมก็ได้ปึ๊บเฮ้ยปินี่
เดี๋ยวสอนผมก็ได้อะว่าทำไง
อันนี้คือถ้าจะใช้แอปอื่นอาจารย์ต้องกดปิดกัน
ครับ
ปิดอันนี้
เอาปิดไม่มีตา
ลงจ้ะ
ครับ
ขึ้นมา
Screen Capture เนี่ยนะครับ
แล้วก็
อืม
เซฟเสร็จปุ๊บถ้า
แต่ว่าเอา
จริงๆลงอย่างนี้เลย
ลบมืออะไรอ่ะ
ลงอย่างนี้นะจะลงเฉพาะจุดไม่ต้องกด
มันไม่มีกดปุ่มออโต้ที่เหมือนเคลียร์หมดกระดานนะไม่มีเลยครับ
มี
อ๋อขยะอ๋อโอเคได้ครับได้ครับขอบคุณมากครับขยะคือลบหมดโอเค now let's consider the next situation we go to the next topic actually which is ปิดอันนี้ไปก่อนนะครับ that's the magnetic field from a current carrying conductor so สวัสดีครับเอาจีน6บอกว่าลา
ใช่ผมลาไปลาไปห้องกันเนาะ
อ๋อ
หมดค่ายังดูไปอ่านก็รอ
we have a conductor here, right? And when the current is inserted from left hand to the right hand, to the right side, okay, from left side to the right side, we're going to observe how the magnetic flux density is induced, right? Okay, we're going to use again the right hand rule. Your right hand is right hand, and you rotate your four fingers according by once the thumb direction is along the way of the current. Okay, okay, two things. Once you have the dot line that represents the head of the arrow, once you have the cross sign or the X sign that represents the tail or the rear part of the arrow. Okay, but yeah, the magnetic field lines will happen like this. Okay, according to this plane, which is the vertical plane, which is cut from this box, this cubic. You can see the front or the head of this arrow, and here at the end, okay, you have the cross section, which is the X side or the cross side, right? Which is the tail or the rear part of the arrow only. Okay, yeah, the magnetic field, magnetic flux density is gonna rotate around this conducting current carrying conductor. Okay, let's consider the first situation. Once there is no current flowing through this conductor at all, which is aligned in a vertical way like this. Okay, when there is no conductor, the magnetic field just stay. The direction of the compass or the needle in these 5 compasses, okay, will be directed in the same way. Okay, in the way of the Earth magnetic field lies, okay, wherever you place on the Earth. But once you insert, let the current flow through this conductor, okay, because the magnetic field which is induced from this conductor is stronger than the Earth magnetic field, so the compasses will be oriented according to the magnetic field induced from this current flow flowing through this conductor. Okay, let's move to the next one. We arrive at this guy, okay, this person. His name is, I'm not sure, I didn't learn French at all. Okay, I didn't learn French before. Okay, Jean-Baptiste Biot. He was a French physicist, okay, and astronomer and mathematician. He discovered Biot-Savart law of magnetostatics. Together with Felix Savart, okay, who is that guy? There is no picture or photo of Biot-Savart, okay, it's only sculpture like this. Felix Savart was a French physicist, okay, he has already passed away. And he was also a mathematician. He is primarily known as B.O. Savard together with B.O. before. And this law is known as B.O. Savard law, right? Together with his colleague, Jean-Baptiste Biot. So what about the B.O. Savard law? It's going to tell you about the magnetic flux density in magnitude term, and it depends on the permeability of free space mu0 and the current. Okay, how strong you insert the current. Okay, if you let the current flow more, there will be more induced magnetic flux density here. The magnetic flux density is stronger proportionally, right? It's a linear proportion. So mu0 is a constant from the measurement, actually. And the point that you observe the magnetic flux density, okay, the further the distance, the weaker the magnetic flux density you can receive. Okay, so it's inversely proportional to the distance from the conductor. Okay, if you stay far from the conductor, you will get weaker magnetic flux density. If you go far and far, you will get very weak magnetic flux density. When you go to the infinity distance, okay, then the magnetic flux density will remain 0 for you. So we get this formula, mu0I divided by 2 pi r. 2 pi r represents the distance around the center of the circle, actually. So let's talk about mu0. Mu0 is 4 pi times 10 to negative 7. And the unit of permeability of mu0 in the free space is Tesla meter per ampere, like this. Okay, and of course the unit of magnetic flux density in magnitude is in Tesla or in SI system. Apart from ampere meter, you're going to have volt second per square meter. Now let's go further. The way to determine the direction of the induced magnetic flux density is to use the right hand again when your thumb is directed to the current movement direction, I here. Okay, and yeah, your remaining 4 fingers will represent the direction of the induced magnetic field, magnetic flux density. R represent the distance from the point that you want to observe the magnetic flux density. Okay, this is the B.O. Savard law, right? Now let's consider an example from this one. ผมก็ว่าละเสียงอะไรฟรีๆ แต่ไม่เป็นไรไม่ต้องไปปลุกเขานะครับ กำลังมีความสุข โอเค โอ้ลบได้จนเกลี้ยงหมดเลยนะ จนแบบหมดเลยนะครับอันนี้เคลียร์เลยอะสุดยอดมากทำได้ด้วยนะครับโอเค anyway we gonna use the อันไหนนะเปิดที่แบบว่าที่จะเขียนอันนี้ป่ะครับแอปพลิเคชันป่ะครับ annotate นี่นะโอเค alright this is the long straight direct current power line that carries the current of 100 ampere. Oh, very strong. A swarm of bees กลุ่มฝูงผึ้งนะครับ builds a hive next to it, and they use the principle of magnetism. The bees use the Earth magnetic field as a reference direction when they wanted to orient their honeycombs, right? Okay, at what distance from the power line? At what distance from the power line is the magnitude of the magnetic field from the current equal to the magnitude of Earth's magnetic field, about 50 micro Tesla. So let's draw what's going on. Is there any figure to that? There is no figure. Okay. Let the copper wire or conductor stay in the horizontal way like this, and there is the current moving through this line with the magnitude of 100 ampere. Okay, this is I. Okay, this is I for us. And then they want to observe the distance, which is R. Okay, in this scenario, we're going to use the Biot-Savart law. This is R, and what is that, right? At this location, we want to get B. B as 50 micro Tesla. Okay. So from the Biot-Savart law, we have B. We have B, right? Mu 0 I by 2 pi r, right? And you want to find r, you need to move r to the left hand side, b to the right hand side. So r will be mu 0. Mu 0 is 4 pi times 10 to negative 7. That's mu 0. I is the current, right? So it's going to be only 100. And you divide it by 2 pi. 2 pi n times b, right? B is 50, so we're going to have 50 times 10 to negative 6 Tesla. Okay, or 5 times 10 to negative 5. Okay, and you just calculate it. The result emerged as 0.4, okay, to pi b. Is that correct? Right. 2 pi, pi and 2. And 2, yeah, 4. Is that correct? 0.1. Number 2, 2. 0.1. So 0.4 meter. So it's going to be 40 centimeter from apart from the current conductor. Okay, 0.4.ต้องปิดก่อนนะครับ Yes อันเนี้ยเซฟไปเลยครับ Okay now let's move to the next one มือรูปตรงนี้ไม่ได้ใช่ไหมครับขึ้นไม่ได้เนาะต้องจาก iPad เอา Now we realize that the next problem, find the current in a long straight wire that would produce magnetic field twice the strength of the Earth and at the distance of 5 centimeter. So you have B, right? You have B. B equal to mu 0 times I by 2 pi r, right? And here they want to know I. You have to move 2 pi r to the left hand side and mu 0 to the left hand side. So we're going to get I equal to 2 pi b r and 2 pi b r by mu 0, right? And here the way to compute further, right? 2 of B Earth, 2 times twice as much as the Earth, right? The Earth's magnetic flux density. So it's going to be somehow the quantity that was shown in the previous example, 50 micro Tesla. So 5 times 10 to negative 5, and r is the distance of 5 centimeter. We're going to need to convert 5 centimeter to meter, which is that 5 times 10 to negative 2. Okay, and the constant mu0 will be 4 pi times 10 to negative 7, and you just compute it by using the hands or the calculator. You're going to get 25 ampere. Okay, no. Okay, let's move to the next figure. We're gonna we arrive at the next topic, which is QB, I think, right? Oh no, ILB. From the previous one of the previous topics, we have the force, right, induced on a charge QVB. We're gonna borrow that idea to the moving charge in the conductor. When the charge moving with the drift velocity, okay, v with d like this, okay, and of course it's move in the same direction as the part of the conductor aligned, okay. When it slides vertically like this, we're gonna have velocity in this way, and please note that the magnetic flux density is represented by the cross sign or the X symbol here, right? There are many X symbols. It means the magnetic flux density is uniformly distributed across this area, okay, on this area. So wherever you stay in this area, you get the same value of the magnetic flux. So this should be assumed, okay, because the charge will move in this area. So from the FQVB, from the previous formula, we have F equal to Q V cross B, right? FQVB, we start from V to B, right, by using the right-hand rule. V, the cross sign or the X symbol represent the tail or the rear part of the arrow, right? So V to B, right? That's the direction of the magnetic flux density pointing into this whiteboard or this monitor, right? V to B, so the time direction will give us the direction of the induced force, so there will be force in this way to the left. Or in another alignment, once we FQVB again, okay, Q, once the conductor is aligned in the horizontal way like this, and again we have the X or the cross symbols here, that represents the rear part or the tail of the arrow of the vector of the magnetic flux density. So the drift velocity will be in the same way as the current. Let's say this is the positive charge, okay? When you talk about the actual particle that moves in the conductor is electron, okay? Not the positive charge like proton at all. But for simplicity, humans usually assume that the positive charge is moving, but it's not the case in reality. So the positive charge moves to the right, and you have V, right? V to B, right? The direction of the magnetic flux density is directed or pointed into this plane, right? So V to B. So we get the induced force pointing upward like this, okay? And let's the part of the conductor that we consider is by L meter, okay? L is the length of the part of the conductor that we are considering. And we will transform this formula from FQB, okay? The QB sine theta, right? V to B, right? V in this way, and B is the direction inward, this plane. So the angle between both vectors will be 90 degrees, right? So we have psi as 90 degrees. When we substitute psi as 90 into this formula, psi of 90 will be number 1, so there will be no trigonometric function at all. The remaining thing will be only the product of QV and B. Vd is the drift velocity, so the average velocity of the positive moving positive charge. Okay, when we have many elements, there will be many forces. Let's say the n charge move, okay, there will be Fn force to that moving charge. And if we have capital N particle, okay, with the same constant speed, Vd, drift velocity, is the group velocity actually. Vd could be found from the total length L. Total length L divided by the time that we want to observe. Okay, this is the length. Speed is the ratio between the distance and time, right? So the distance is L, and the time is the time that you observe is, let's say, it's delta t. So Vd is L by delta t right here. And in this case, let's consider the situation when a part of the conductor is lying in the area of the magnetic flux density that is directed into this plane. Once there is no current, I is equal to 0, there will be no force at all. But once there is current moving upward like this, okay, the conductor is going to be bent a little bit. It's going to bend a little bit. Why to the left? Because let's say the positive charge is moving like this, right, upward, and magnetic flux density is directed into this plane, okay, V to B. So the direction of the induced force will be to the left, right? So that's why the conductor is a little bit bent to the left. And once in the opposite way, once the current is moving downward, the drift velocity is going to be V in this way, right? V to B, right? V to B, right? So the induced force will be to the right. That's why the conductor a little bit bent to the right. Okay, it has a curvy shape to the right because of that. Now we move to the total amount of the moving charges. Let's say the capital Q. Capital Q is the summation of all charges, all particles. And in terms of ampere, the current is the ratio between moving charge per time, right? I is Q by delta T. So the total force could be found from the summation of every force. And each force is the product between Q and VDB. There is no sine theta at all because theta is 90 degrees, so sine of 90 is number 1. We ignore that. V is L by delta T, right? And summation of Q is capital Q. Q times L by delta T. I delta T by 33, right? That's the Ampere law. So we're going to have I delta T, L by delta T. Delta T will cancel each other. We're going to get ILB. That's why we have the formula ILB in this scenario. Note that the total force in 34 is valid when the angle between the charge and the magnetic field, charge motion, is the right angle or 90 degrees. But if there is a certain angle, when the angle is not 90, let's say theta, when theta is not 90 degrees, what happens? ทำไมไปต่อไม่ได้ครับ iPad ผมเจ๊งเหรอไปได้นี่ก็ไปได้แล้วครับ Okay, when theta is not 30 degrees, 90 degrees, what happens? So theta will be a variable that can change, right? When the current moves in this way, okay, there is an angle with respect to the magnetic flux density direction, phi b, phi like this, okay. We would have the perpendicular component is b with subscript perpendicular side symbol, right? B side, and this is b parallel, right? The component that is meaningful to us is the one that is perpendicular, that is F, right? V, B, right? So we decompose it into B perpendicular and B parallel, but the one that is meaningful is the perpendicular one. So this is the vector of I, right? Vector of L, I, L, B, right? This one. So the induced force will be directed upward like this. Okay, for a given angle phi, we would have F equal to ILB, that is the perpendicular component. But the perpendicular component could be found from B side phi. So this can also be represented as the vector cross product, like FILB. L is the direction of the current moving in the conductor. Okay, L vector like this, and B. Okay, B, this one. Okay, you just cross it, get the induced force direction. And phi or theta is the angle measured from the first vector, which is vector L, to vector B. Okay, you get the cross product formula. And here we would have LB again. Okay, L and B, the induced force is upward, in the upward direction. In this scenario, ILB, L is in this way, and B is in this way. Okay, we're going to move from L to B. Induced force will be downward. And in this scenario, we have L and B, right? L in this way, B in this way, L, B. The induced force direction is upward. So what is the application of the magnetic force on a current carrying conductor? That's the speaker. Okay, speaker appears everywhere. Okay, when you want louder signal, okay, when you want a louder signal, you're gonna need amplifier and loudspeaker. Okay, loudspeaker is made of a certain several numbers of the conductor loops like this. Okay, it's current, and that's loudspeaker. Let's say we have permanent magnet that has the north pole in the middle and the south pole at the two edges. Okay, at the upper part and the lower part. And of course, the magnetic field line will start from the north pole to the south pole. Each this bar, okay, will create the magnetic field upward and downward like this. Okay, and because this is the conductor loop, right? When the current move in this way, okay, this move out of the plane, because we have the circle dot here that represent the head or the front view of the current movement, current direction. This is the tail part or the rear part, the tail or the rear part of the conductor movement. So that's why we get the cross sign or the X symbol. Okay. Of course, at this location, you would get vector V, vector L like this, right? L and B, right? L and B. L, B, so the force will be induced in this way. Okay. At the lower part, the L vector will be in this way, right? And the B vector is downward. So LB, you get also the force directed to the left. So the total induced force to this paper cone will be to the left, okay, to the left direction. And how often or the frequency that is made to this conductor, okay, will produce music and so on, several voice or voice of human speaking into this paper cone. And the paper cone will compress the air when there is stronger current. When the current is stronger, the paper cone will compress better, and that's why we get very loud sound, okay, because of the compression of the air by the paper cone, which is controlled by the current, okay, the current loop in this speaker, okay. That's the prominent application to the loudspeaker. ทำไมเจ๊งอีกแล้วครับน่าจะเป็น iPad ผมแหละเลื่อนไม่ได้เลยนะครับ Okay. Now we move to the next slide. We arrive at a promising example. That's a bird, right? The smallest or the lightest bird is hummingbird, right? Its mass is only 1.6 gram. It's very light. น้ำหนักน่าจะเท่ากับแมลงวันมั้งประมาณนี้ 1.6 กรัมผมก็ไม่เคยชั่งแมลงวันนะแต่ว่ามันคือนกนะครับนกมันก็ต้องมีกระดูกสันหลังเนาะแมลงวันไม่น่ามีกระดูกสันหลังนะครับ Okay. So there is a bar which is made of metal and the mass of the bird is 1.6 gram and the question is we don't want to hang these perch by using any structure. We're going to use the magnetic force, okay, according to our theory in this problem. ILB, all right. And how much current we need to let it flow through that perch or conductor. Okay, let's talk about the detail. In figure 46, the perch should be strong enough to support the perch itself and the bee hummingbird. And we use the magnetic force to support the perch for this bird. The perch has the length of 10 centimeters. It's not so long. And its mass is 7 grams. It contains a wire carrying conductor contains a wire carrying a current of 4 ampere. So what are the direction and magnitude of the magnetic field should be so that the whole system remains stable? Okay. In this scenario, right? I is 4, the length is 10 centimeter. Current is 4 ampere. Current here, I, is 4 ampere. And the length L is 10 centimeters. In SI system, you're going to say it's 0.1 meter, right? So there should be magnetic flux density, right? But you know that the weight of both particles, the bird and the perch, should be combined as the W weight, right? The quantity W. And in order to get equilibrium state, okay, everything should be in the static equilibrium. So it means the force upward here, the upward force should have the same magnitude as the downward force, which is the weight. In order to get the magnetic force induced upward like this, you're going to need the magnetic flux densities for a certain direction, right? In order to get the upward force, and L is like this, so B should be directed into this plane, okay, V to B, so we get the upward force. We're gonna compute what is the value of B, right? But before we go that, you need to use the equilibrium state from the Newton laws, right? F upward. The upward force will be equal to the weight of both particles, the birth and the purge. 1.6 and 7, right? So 1.6 plus 7, but you need to convert gram to kilogram is times 10 to negative 3. Negative 3, right? That's M and T is 9.8 meter per second square second. That's the force, right? And F equal to ILB. If you want to find B, you need to move I and L to the left hand side. B will be F, which is the amount here, 7.6 times 10 to negative 3 and times 9.8. That's the acceleration, G, gravitational acceleration on Earth. And then I and L, right? I is, I think, 4 ampere. And L is, no. L is 0.1. 0.1. Okay, and then, yeah, that's it. Just move it, use the calculator to compute. 4 ampere, right? So you will get 0.2107. 0.211. 107. The unit for this is Tesla. For magnetic flux density is Tesla. All right. This one. For this problem. Okay, now we move to the next thing, which is the next example. A wire carries a current of 22 ampere from west to east. Okay, let's say this is conductor and direction is from west to east, right? From left to right. I is 22 ampere. Okay, and assume that the magnetic field on the Earth at this location is horizontal and directed from south to north. So B, from south to north, like this. Okay, that's B. And it has a magnitude of 50 micro Tesla again. Right? Or 10, 5, 150. Okay, this is 50 micro Tesla. Find the magnitude and direction of force when the length of this conductor is 36 meter. Oh, it's quite long. 36 meter. Yeah, that's L, right? So if ILB, again, I is the current, which is 22. L, the length, which is 36. B, the magnetic flux density, are 0.5 times 10 to negative 4. Okay, and 1/2, 11, 36, 33, and 60, right? 390, 390 times 10 to negative 4, and it's going to be only 0.039 unit is Newton. It's not strong, right? It's less than 1 Newton. Let's check whether it's correct or not. It's wrong. Yeah, it's correct, 0.039. But there is another question as well. Calculate there is another question. Calculate the gravitational force on the same length of the wire when density, yeah, they should provide the density and cross-sectional area. Of course, the weight is computed from W equal to mg, right? W is equal to mg, but m could be found from, you know that rho or d, the density is m by v, right? If you want to find m will be rho times v, density and volume. But the volume in this case is the cylindrical, right? It's pi r square h, the length. Actually, it's not h. It's L, length. So m will be rho, right? V is pi r square L, and G is only the constant. It's not difficult. Rho is 8.92 times 10 to 3. Pi is pi, right? 22 by 7. And I is the radius. They don't say radius is, it's V and L, right? This one, pi r square, which is representing the cross-sectional, and this is A and L, okay? A and L. So we don't have to use pi r square at all. Oh, no. We have to remove this. Okay. Pi, and then A, which is this one, 2.5 times 10 to 6. And L, okay, L is the length. The length of this conductor is provided in previous 36. Okay, 36, and G is 9.8. Okay, 9.8. You leave it in the leave them in the calculator. You're gonna get 7.86 Newton. Okay, it's approximately 7.87 Newton. All right. That's the force caused by the Earth, or the gravitational force on Earth. Okay, now let's move to the next example. The time is over. Okay, that's the next topic, right? Magnetic force between two conductors. I think it's time for you to have homework, right? Because there are many examples, ILB formula, for example. Okay, ก็กันบ้านนะครับ ให้เลือกโจทย์1โจทย์นะครับ ที่เป็น FILB นะครับ FILB 1 ตัวอย่างนะครับ เดี๋ยว create ใน Google Classroom นะครับ แลกกันหน่อยนะ คะแนนเก็บนะครับ โอเค see you on Wednesday, right? Next Wednesday. บ๊ายบายครับ สวัสดีครับ ห้อง4ไม่ต้องแล้วนะครับ รวดเดียวไปเลยนะครับ ไม่ต้องไปแล้ว ก็เก็บของกลับบ้านกันได้เลยนะครับ แต่ผมไม่รู้ว่ารปภจะให้คุณกลับหรือเปล่านะครับ แบบนี้พวกนี้ก็ได้แล้วก็เปลี่ยนเลขเอาก็ได้ครับขอ ILB นะครับ1ข้อนะครับแล้วก็จะถ่ายรูปก็ได้หรือว่าจะเป็นแบบเขียนบน Good Note ก็ได้ iPad ก็ได้ถ่ายรูปก็เป็น PDF นะครับเอาอัพขึ้นใน Google Classroom นะเดี๋ยวผม create ไว้นะครับถ้าออกไม่ได้ก็ขึ้นรถผมไปก็ได้นะครับโอเคไหมเดี๋ยวผมปิดกระจกแล้วก็รอพอก็ไม่เห็นแล้วคุณก็ออกไปเดินข้างนอก